welcome all of you. And since last couple of classes, we started discussing about solid state NMR. As I was telling you, solid state NMR spectrum is slightly different from that of the liquid state NMR spectrum, because the interaction parameters are different here. So the way we have to do, to operate and average out the anisotropic interactions so that we get sharp lines is different here. Whereas in the case of the solution state, there is a natural thermal motion going on and there is a natural averaging of the anisotropic interactions. Whereas in the case of solids, it does not happen like that. So we need to do our own way, adapt a strategy to see that the second rank tensor components like tensor interactions, like heteronuclear dipolar couplings, chemical shift anisotropy, all those things we need to average out. I said one of the ways is by doing physical averaging, where we can do this spinning of a sample, keeping the material in a rotor at particular angle called magic angle, which is 54.7 degree with respect to the magnetic field. And after stationing the rotor in that angle, keep on rotating at a very high speed of the order of several tens of kilohertz. Then I also mentioned to you the average orientation of all the internuclear vectors will be deemed to be under the spinning axis, which is making an angle of 54.7 degree with respect to the magnetic field. And this, when you look at the parameter, I said it depends upon orientation parameter called 3 cos squared theta minus 1 by 2. So as a consequence, what happens if you put the 54.7 degrees in the T equation, it goes to 0. So the dipolar coupling can be averaged out by physically rotating the sample, keeping the rotor at magic angle. That is one way. And it of course cannot eliminate homonuclear dipolar couplings. It can eliminate only heteronuclear dipolar coupling and chemical shift anisotropy. Now also I said we can combine this to heteronuclear decoupling also. That is one thing. And for homonuclear dipolar coupling, the averaging can be done in spin space. Identical strategy you can adapt, where you can keep on applying the radio frequency pulses with the specified delays between them, such that the magnetization or the spins spends equal time on all the 3 x, y and z axes. What happens at that time? You have to keep on applying the RF pulses rapidly, ensuring that the magnetization spends equal time on all the 3 x, y and z axes. You are basically creating a sort of a cuboid. And identically even for the magic angle spinning also, you can now imagine this should be under the cuboid, and if you will take the body diagonal of the cuboid, it makes an angle of 54.7 degree with respect to any of the 3 x, y, z axes. Similarly, in the averaging the spin space also, it is, you can imagine to be magnetization or the spins aligning along the body diagonal of the cuboid. So in other words, both these averaging processes can be treated as dynamic implementation of the cubic symmetry. That is what happens. So these things we discussed, and I also said abundant spins, for example proton and fluorine, you cannot eliminate the homonuclear dipolar coupling, they are homogeneous interactions very easily by magic angle spinning, and we have to resort to combined effect like magic angle spinning and also Wah-Hoo-Ha sequence, where averaging can be done in the spin space. Varieties of things are there. That is what we discussed also. And I said practically most of the nuclei other than proton and fluorine can be considered as dilute spins, and that is what is normally focused upon in routine applications. And high resolution for the proton and fluorine are generally not so easily you can obtain the high resolution, in spite of all the advanced techniques developed by various stalwarts in NMR. As of now, the maximum line width or minimum line width we can get is of the order of 40 to 45 hertz. So it is still far away from what we can think of getting a high resolution NMR spectrum like liquid state. So as a consequence, most of the studies are restricted to dilute spins. So I said dilute spins, like for example, if you take carbon 13 in organic systems, we can detect carbon, but carbon is less sensitive Gyno-magnetic ratio is 4 times less than that of the proton. So, direct detection takes enormous amount of time due to less sensitivity. So, I said there is some way we can do, we can adapt a strategy. Remember we discussed the polarization transfer technique in solution state, which we adapted for inept sequences in HSQC etc., where the proton magnetization is transferred to dilute spin. Identically, we can do that in the solid state also. In the solution state, you use the mechanism for the transfer is antiphase terms we discussed arising because of the J couplings. Now, here in the case of the solids, this can be done by using what is called dipolar couplings. Same technique we can adapt. Similarly, we can take the magnetization of the abundant spins and transfer it to the dilute spins. It is possible, and this is called cross polarization. So, today we will discuss about the cross polarization pulse sequence and see how we can enhance the signal intensity and all some cross polarization dynamics we can discuss. So, this is the cross polarization pulse sequence, very simple. Apply 90-degree pulse on the proton channel, bring the magnetization to y axis, and now you are in the rotating frame, and at the same time simultaneously apply RF pulse in the same direction on carbon 13 spin. Now, the magnetization is along y axis, apply RF pulse along y axis, same for the X nuclei also. Remember I earlier said it is as analogous to spin locking. When I was discussing TOCSY, I discussed this. It is like spin locking. So, you can lock the spins. Now, both the spins are independently you are applying pulses and mixing pulses and bringing them into the contact. You are in the doubly rotating frame, and something will happen during this mixing time between the two nuclear spins like proton and carbon. We will discuss that later, and then start collecting the signal after mixing time while simultaneously doing the decoupling of protons. So, you are going to get the carbon 13 spectrum which are fully decoupled, broadband decoupled, but at the same time there is sensitivity gain because of cross polarization. And what is the duration of this cross contact time? Duration of the spin lock, it is of the order of few milliseconds. Remember, few milliseconds. So, during this time there is a polarization transfer that is taking place between proton and carbon, and proton magnetization of the abundant spin will be transferred to carbon 13 magnetization. How it happens, let us try to understand the concept. Let us say what is the magnetization at equilibrium before the application of the 90-degree pulse. Before application of 90-degree pulse, as you know, before applying any pulse on either proton or carbon, both proton and carbon are in thermal equilibrium. That is correct, that we know. And what is the energy separation between these two? We know this energy separation, this is for the proton and this is for the carbon, and carbon is 4 times less than that because of the gamma, 4 times less energy separation. So, if you go to a, let us say 600 megahertz magnetic field, at the resonative frequency for this magnetic field, resonative frequency for proton is 600, in the same magnetic field resonative frequency for carbon is 150 megahertz. This we all know, and energy separation also we know is 1:4. Now, with all those things are fixed, gamma, B naught is fixed, gamma is fixed, gamma are fixed. Now, Z1 energy separation is very much different from proton and carbon. You cannot make them equated in the thermal equilibrium in the conventional way. If you just put the sample, there is no way you can even equate the energy level between these two, but we can do it in a doubly rotating frame in a different way. Before that, let us try to understand the spin temperature concept. Let us look at proton spins. I call them I spins. Before the application of 90-degree pulse on protons, what is the magnetization of proton? Where is it? It is along the z axis. The static magnet in the static magnetic field, magnetization is along z axis, and we say the spins, proton spins, are at what is called the lattice temperature. In thermal equilibrium, it is at a lattice temperature before application RF pulse. This is what you should remember. Okay. Now, what happened to the carbon spins? What is, for all practical purposes, we can assume there exists no net magnetization of the carbon spins. Why? Because the net magnetic, the chiromagnetic ratio of the carbon is much smaller than that of the proton, and because of the very long spin relaxation time, practically you can assume there is no net magnetization of protons, of carbons at that time. Okay. Now what does it implies? The population between two spin states are equal. When there is no net magnetization means what? It is like saturation, that is what we discussed also. When there is no net population difference, that means both the energy states are having equal population, it is called a saturation state. When this can happen? I will discuss the spin temperature concept earlier also, I will also discuss today. This can happen only at the temperature T, which is at infinity. At infinite temperature, we can say that population between two energy states are equal. This is the Boltzmann population difference. You can see, if you look at the ratio of the N2 by N1 population difference, then S carbon spin can be considered to be infinitely hot. You understand? S carbons are considered to be infinitely hot just because I am considering they are less Gaia-Magnet ratio and long relaxation time. So, I will assume it is like this, it is infinitely hot. What about high spin magnetization in the XY plane now? We come to XY plane. Before application of the 90-degree pulse, due to random approximation, there exists no net magnetization in the XY plane. That will also be discussed. Random phase approximation in the first or second class itself we discussed. There won't be any magnetization in the XY plane, and in thermal equilibrium magnetization is only along Z axis. So, Mx is 0, My is equal to 0, only Mz is present. So, the projection of the high spin magnetization in the XY plane is 0. Again, what does it mean? In the rotating frame or in the XY axis, if you consider, the spin temperature of high spins is also effectively infinite. You understand? The spin temperature of high spin is effectively infinite. Correct. Now apply a 90-degree pulse on the high spins. Bring the magnetization to XY plane. Like this. Apply magnetization 90-degree pulse, bring the magnetization to X axis. One of the axis X or Y, depending upon where you apply the pulse. Now immediately apply RF pulse in the same direction. If the magnetization is brought to X axis by applying a RF pulse, in the same direction apply B1 pulse, RF pulse, and then magnetization gets locked. This is what we said. This is called locking, spin locking. You can bring the magnetization to X axis, apply again the RF field in the same direction, B1 field, then they get locked. This is called spin locking. So, now what is when it is in this rotating frame? Now we are in the rotating frame. In the spins can still relax in the rotating frame, even though it is locked. It can relax, but in its own relaxation time, that is called T1 rho. It has its own relaxation time, rate of relaxation. This is T1 rho. T1 rho is called spin lattice relaxation in the rotating frame. Remember, we are already in the rotating frame because when we have brought the magnetization in the XY plane, rotating frame concept we discussed long ago in the previous course. Extensively it was discussed. Those who have not taken that course, please look into that. So, what is the order of T1 rho? It can be comparable to T1 of protons. Okay, much. Usually in solids T1 is very long, but it is T1 rho is, if you consider, T1 rho is much better. You can much smaller compared to that of the T1 or T2. The magnetization decays in the RF field. Magnetization decays only when the RF field is turned off. That is the natural relaxation time. When the RF field is turned off, when it is locked, that the relaxation is T1 rho. Okay. So, you say magnetization is locked. That is one thing. Now, we will understand Zeeman energy levels in the rotating frame during spin lock. This is the Zeeman energy levels even in the rotating frame before equating this, before some condition which is attached. You have brought the magnetization of proton to let us say X or Y axis. Simultaneously you apply radio frequency pulse on the carbon 13 in the rotating frame in the X or Y axis. Both simultaneously you apply pulse. Now still the energy levels remain same. You have not changed anything. Okay? But only thing is now the separation, instead of what it was, it used to be gamma H into B0, now it is B1, that is all. RF power of the carbon 13, here RF power of the proton. Earlier in the thermal equilibrium, it was energy level separations is comparable and you have to deal with B0 magnetic field. Okay. So, in thermal equilibrium energy state and in the rotating frame, they are different now, that is all. But still Again 1:4 difference is still there. But then what we will do is, now I can adjust the spin lock power. See, when the thermal during the at room temperature, or when the magnetization is along z axis in thermal equilibrium, energy separation you cannot equate them, because whatever you do, you change the magnetic field, simultaneously the energy states, the energy difference between both proton and carbon changes by equal amount, linearly it changes. Whereas in the rotating frame, now this is the formula. So B naught I do not want to change, I cannot change, but B1 I can independently change, that is possible. So in the rotating frame, what I can do is, I can rotate B1 of proton, I can change B1 of proton or B1 of carbon 13 and adjust it. How can I adjust that? I can manipulate this in such a way the energy levels become equal. It is possible. So I can do that, and this condition is called Hartmann-Hahn condition. Hartmann-Hahn condition is gamma of carbon 13 into RF power B1 of carbon 13 is equal to gamma of proton into B1 of proton. Okay, this is called very famous Hartmann-Hahn condition. Okay, and now when you match this condition by adjusting the RF power of proton or carbon 13, what is going to happen? Look at this, energy levels become equal. I can manipulate it. RF power I can manipulate in such a way the energy levels of both proton and carbon become equal. Now the RF here omega 1H is of the order of 50 to 100 kilohertz, here also 50 to 100 kilohertz. I equated it. Earlier it was much larger, in B1 B naught field it was of the order of megahertz. Now it is only few kilohertz, and I have equated these two. And now we have entered into what is called a doubly rotating frame. In the doubly rotating frame, I tune the RF power of either proton or carbon and ensure that the energy level separation between both of them are equal. Then what will happen? Logically you can say, when there is no difference in energy level between proton and carbon, they behave like identical spins. They lose their identity. Then you do not know whether it is a proton spin or a carbon spin, because energy separation between both of them are same. So that is what happens in the doubly rotating frame. Now you have created a situation, the energy levels of proton and carbon are same, both the spin behave like identical spins, lose their identity at all, completely lose their identity. There is no identity for them. Now at another thing, let us understand what happens when you make the energy level equal, energy levels between of proton and carbon when they are equal in the doubly rotating frame, what is going to happen? Let us understand now. At equilibrium, the huge magnetization which was there, at equilibrium energy separation was larger because it was under B naught magnetic field. Right? Now that was the real Boltzmann distribution which is given by Boltzmann population difference. So at then which was in thermal equilibrium, this is the population difference. Very small population difference, we discussed that. More spins are in this state and less spins are in this state, but the difference is negligibly small. Now during spin lock what happens? The large magnetization of the proton is held by a small field. Instead of B naught, it is held by B1 field, RF field, which is very weak. Compared to megahertz, it is 50 to 100 kilohertz. Where is megahertz, where is kilohertz? That is the advantage. So now the large magnetization is held by the weak RF field. How do you understand that? It is as good as I told you, when the magnetic field increases, the energy level separation increases. But now this population difference is same, but you reduce the magnetic field, it appears as if they are compressed. Energy levels are compressed with similar population difference, same population difference. So it means the Boltzmann population distribution appears as if it is at lower temperature. You have reduced the temperature. That is what it means. So that is the implication. Still you have a Boltzmann population difference, but it appears you have lowered the temperature enormously, so that more spins are in the lower energy state. Okay. So the apparent Boltzmann distribution in the rotating frame is, when you bring the magnetization here and apply a radio frequency pulse along this, during the spin lock, now the energy level separation has reduced, become much smaller. It is compressed. It is now held by a weak RF field. But you see, more populations are there in the ground state now, the lower energy state than the higher energy state. Much more. That is what happened. So now you can say there is excess population in the ground state. What did you do? By going to the rotating frame, by applying the spin lock pulse, it apparently there is apparent distribution of the magnetization, Boltzmann distribution. It appears as if the energy levels are compressed and large population difference which was there in the B naught magnetic field is held by a weak RF field. That is what it is. Now spin temperature during the spin lock, what is happening is a large magnetization is held by a relatively weak field for proton. This situation corresponds to large difference of spin population between 1/2 and -1/2 abundant spin. It means, as I said, it corresponds to low temperature. It is as good as telling protons are at very low temperature. By doing spin lock, during the spin lock, protons are at very low temperature. That is what it means. Spin locking lower the spin temperature of protons. Okay. This is the situation just before establishing cross polarization or establishing Hartmann-Hahn condition. That you remember that. Now what is the temperature we have lower? How much is the lower temperature now in the spin lock? Remember, at lattice temperature in thermal equilibrium is at 300 K. Just calculate it in the 500 megahertz spectrometer. The RF power we apply is 50 kilohertz. Where is 500 megahertz and where is 50 kilohertz? So temperature of the protons now will be around 0.05 degree Kelvin. Instead of 300 K, it is drastically reduced. It is at 0.05 K. That means when you are doing the spin locking, you have made the spin systems of the protons become extremely cold. Now the proton spin system is extremely cold spin system. Fine. What about the carbon spin? Carbon spins are S spins. They are hot, very hot. Why? Because there is no net magnetization in the XY plane. There is no magnetization at all in the XY plane. I have not applied the RF pulse and brought it to this thing yet. So apply now spin lock pulse to S. What will happen? When these Y spins are locked, at the same time apply RF pulse on the spins, on the S spins, carbon 13. Now you adjust the RF power and equate them. What is going to happen? S spin, because of no net magnetization, it is at infinite temperature because you can say population difference is 0, it is a saturated state. But proton is at cold temperature, very cold. Now carbon is very hot. What happens if you bring them to contact? When you bring them to contact, then there must be exchange of heat between two systems. Now there are two thermal bodies. One is at a very cold temperature, one is at very hot temperature. Bring them to contact now. There must be exchange of heat, with exchange of energy in the form of heat. Okay. Now proton being very cold system would receive the energy from the hotter system. Then while receiving, what will happen? It will give its magnetization to carbon. In the process of the conservation of the energy, proton gives its magnetization to carbon 13 because it is very hot. Thermal equilibrium you are trying to establish between these two spins in the rotating frame. Now this is what happens. Now it is at 50 kilohertz, this is at 50 kilohertz. Now we match it. Okay. So the transfer of magnetization takes place as extremely hot carbon spins get cooled by receiving energy from protons. So I spin gives energy to S spin. That is what is called cross polarization. You are transferring the polarization of protons to carbon 13. Analogous to what we discussed in the solution state, where by using J coupling, using antiphase terms, we transfer the magnetization from two J coupled between two J coupled spins. Identically here, consider the two thermal paths. One is proton, other is carbon. Now by some mechanism we had brought them to contact and made the spin system to lose their identity. Then carbon, which is at very hot, proton which is at very cold, when you bring them to contact, there is the transfer of magnetization from proton to carbon, and it will try to heat up, and carbon try to cool down by itself. This is what happens. This is called cross polarization. So now if you understand what is cross polarization spin temperature, carbon 13 spin take proton abundant magnetization and gain in the carbon 13 signal. Very large amount of gain in the signal. Okay. Now the thermal contact ensures the flow of magnetization. Okay. When RF stimulates meeting condition like Hartmann-Hunt condition, when it is stimulated, this condition is met by stimulating with the RF pulse simultaneously you are applying in the XY plane while doing spin lock. So the proton gains carbon 13 gains signal. Then what happens to proton? It will lose energy. Huge bath, proton bath you can consider like a big ocean. You take just a mug of water from ocean, nothing will happen. You don't lose anything. You don't feel it as a loss. Whereas the gain for carbon is enormous. That's what is going to happen. Then when you match this Hartmann condition, this is happening. But one more thing you should also understand. We are establishing the contact between proton and carbon. They are not isolated systems. They are also with the lattice. Okay? Simultaneously, they also exchange energy with the lattice, not only between themselves. Proton can give energy to the lattice, carbon can give its energy to the lattice. This is also happening. This is the relaxation process in the rotating frame. That can also, T1 row of proton is there, T1 row of carbon 13 is also there. That is going on simultaneously. Okay. So both have their own relaxation time, they are different. T1 row of proton is different from T1 row of carbon 13. This process of giving its magnetization to lattice, that is going on. Simultaneously there is a transfer of magnetization between proton and carbon 13. Okay. So what is the mechanism of CP? This is what happens. This is the diagrammatically you can find carbon 13 is a hot reservoir, proton is a very cold reservoir. Now you are bringing them to hand, they are shaking their hands, bring them to contact in the rotating frame, they lose their identity. When you match the Hartmann condition, the magnetization transfer goes from proton to carbon. Because it is hot, it wants to cool down, and this will give it to this will try to make sure that proton gets heated up. In other words, this will get cooled down by getting energy from proton. Simultaneously, this is also going on. Relaxation, they are giving energy with the thermal environment, that is lattice. Okay. Now you may ask me a question, fine, what is that mechanism which drives the polarization transfer? How it happens? Spins talk to each other, they give energy, but how? What is the mechanism? Remember, there is a heteronuclear dipolar coupling, carbon and proton. This heteronuclear dipolar interaction, this couples proton and carbon reservoirs. I have proton bath here and a carbon bath here, and the energy transfer from proton to carbon takes place between these two baths using dipolar interaction. Heteronuclear dipolar interaction, that is between proton and carbon dipolar interaction, this energy transfer takes place. And homonuclear also is there, like proton-proton dipolar coupling, that couples with the lattice and causes what is called T1 row relaxation. I told you the spins also interact with the lattice and gives its energy to that. That is T1 row relaxation. Okay. And this is the exchange of transfer of magnetization from proton bath to carbon 13 bath by using heteronuclear dipolar coupling, that you should remember. So what drives the polarization transfer? The equilibration lowers the spin temperature of carbon, and carbon polarization starts increasing initially. As soon as you bring it into the contact, carbon starts gaining a magnetization, becomes more and more increases. And at the same time, it also gives energy to the lattice. It is two simultaneous processes are going on. It is taking energy from proton and also giving to the lattice. This is a dynamic process, and it takes initially for a short time, it takes from proton. But if you wait for a long time, whatever it has gained, it will give to proton also, give to the lattice. That is what happens. So T1 row is also matters in addition to polarization transfer. So during CP, both polarization transfer between I spin and S spins and to lattice are happening simultaneously. Remember, there is a simultaneously transfer of magnetization from proton to carbon, and also from proton to lattice and carbon to lattice is going on simultaneously. And they are changing the magnetization of protons and carbons is given by this equation. which there is no need to derive this. It is available in the books, you can see. And this is what is called a CP condition. Okay. And these T1 rho S and T1 rho I are the relaxation times in the rotating frame. You understand? Simultaneously that is happening and losing energy here. So T1 IS is the contact time, that during which you are going to establish cross polarization, mixing time. Cross polarization time is CP time, which is T of IS. So classical description of cross polarization uses concept of spin temperature. That is what you have been discussing. Please understand, we use this concept of spin temperature to understand the classically what is cross polarization. Now, is this method valid always? True, there are some assumptions you have to make, like in any mechanisms. This approach is valid as long as the system contains large number of spins. You can't have an isolated spin and come to this conclusion. You are considering the bath of spins, huge thermal bath of proton spins and carbon 13 spins. You should have a large number of spins, and the strong proton-proton dipolar couplings also should be present. Then CP also works on isolated spin phase very rarely, and CP also works with suppression of proton-proton dipolar coupling during spin lock. And this assumption, whatever the approach we give classically description, is valid when you have these things. Polarization transfer depends on gyromagnetic ratio of abundant spin and rare spin. For example, ratio of abundant spin to I is abundant spin, S is rare spin. If gamma and gamma S is the ratio, if you take proton and carbon 13, the enhancement ratio is 4 times. Remember, 4 times you gain in the signal to noise ratio if you establish Hartmann condition and do cross polarization. On the other hand, if you take proton and nitrogen, you get 10 times enhancement. If you go to silicon 29, you get 5 times enhancement. So CP results in significant enhancement in the signal intensity. By using cross polarization technique, we can enhance the signal of dilute spins. If you enhance the signal of dilute spins, there is a distinct advantage. You collect the signal at the faster time, where experimental time drastically reduces. Okay. So experiment is faster, and as the T1 of the carbon is of the dilute spin or T1 of proton are both comparable and much smaller than the T1 of the abundant proton. So this is where you have to understand the growth of magnetization during cross polarization. Initially it increases like this, and after some time it starts giving its energy to the lattice. This is a spin lattice relaxation. This is a gain in the signal intensity. You understand? Initially there is carbon 13 signal intensity keeps on increasing, and after some time it gives its also to the magnetization to the lattice and starts relaxing. This is T1 relaxation in the rotating frame. Whereas in the case of the protons, straight away start decreasing because it start giving its magnetization to carbon 13. So it means CP, it is very difficult to say quantitative. You can design a quantitative experiment, but it is not easy because it depends upon the mechanism of magnetization transfer between proton and carbon. So varieties of things you have to understand, but please remember the CP is not necessarily a quantitative technique. So a build up of signal intensity as a function of contact time, if you look at, for example, for glycine magic angle spinning spectra, if you take at 5 kilohertz, see how it starts building up as you keep on increasing the contact time in milliseconds. Contact times are always in milliseconds. You cannot give larger time, then you will burn the probe. So let us say 0.2 millisecond, like that, keep on increasing, you see the signal intensity starts growing like this. This is for C alpha proton grows like this. So there is, you have to adjust the contact time appropriately, and a signal intensity keeps building. You have to adjust the contact time so that is the maximum gain in the signal intensity. This you have to adjust manually. So polarization build-up starts initially, and after some time when it reaches maximum, it starts decaying. This is what I said, carbon 13 increases and then start decreasing. So this is a simple comparison of spectrum with and without cross polarization. A silicon NMR of this molecule, you look at it, this is magic angle spinning, this is one pair CH3 proton, this is another silicon, this is CH3 attached to Si attached to CH3, this is this silicon. Look at this one, this is without cross polarization, just magic angle spinning. Now when you are doing the cross polarization, I told you for silicon enhancement is nearly 5 times, because gamma I over gamma S for when it is proton and silicon, this is proton and this is silicon, it is 5. So 5 times you see the enhancement here. Fantastic, huge gain in the signal intensity. So you consider, look at this alanine, histidine, some powder. This is the carbon 13 T1 is 18 seconds. This is the experimental time. Normally it is done with 8 minutes. This thing, okay, delay of 2 seconds here, and this is with 2 hours and 50 minutes delay of 60 seconds. The advantage, this is with the cross polarization. This is without cross polarization. Now, very enormous gain in the signal intensity is there, and reduce in experimental time drastically. From 2 hours to 50 minutes, it came to 8 minutes and 2 seconds. So this is where you can start comparing. Okay, I think this I will discuss later. I need to explain more for that. So what I am going to do is, I will stop here. We will come back and continue with this in the next class. Today we understood the CP mechanism, where the polarization transfer takes place between proton and carbon. When you establish the Hartmann condition, the protons in the rotating frame are extremely cold, carbon 13 are extremely hot, establish a thermal contact, then what will happen? The carbon 13 wants to become cooler by gaining the magnetization of the proton. Essentially its intensity goes up, and this phenomenon we understood, and simultaneously we also understood T1 rho is there. The spins are also giving energy to the lattice, in addition to carbon 13 gets magnetization from proton. So that is one thing we understood. And the build up curve also we saw how magnetization is going to build up during the CP. Initially it builds up and then slowly start decaying because of the relaxation by its interaction with the lattice. And we saw the gain is enormous depending upon the gyromagnetic ratio. For proton to carbon it is 4 times enhancement, proton to nitrogen 10 times, proton to silicon is 5 times, depends upon the gyromagnetic ratio. And that is what we saw, and we will come back and continue further, where I will discuss much more about the CP and few examples we will look at it. So thank you, I will stop here.